All right. Well, as people file in, I can at least start our intro. So, hello everyone. Welcome. My name is Matt Schumann. I'm a programming librarian here at Cary Library in Lexington. Before we begin, please let me know if you're experiencing any technical issues, and I can try to help you out. You can just message me in the chat. Lost my window there. If you have any questions tonight, please use the Q&A button. And we'll be able to answer those at the end. And lastly, this program is made possible by the generous donors to the Cary Library Foundation, as well as in partnership with Tewksbury Public Library and Belmont Public Library. So thank you. With us this evening is Dr. Kimberly Arcand. She is an expert in astronomy visualization and has been a pioneer in 3D printing and extended reality applications in this field. Dr. Arcand began her career in molecular biology and public health before moving to NASA's Chandra X-ray Observatory with the Center for Astrophysics and Harvard and Smithsonian in 1998. In addition to being an award-winning producer and director, she is an expert in studying the perception and comprehension of high-energy data visualization across the novice-expert spectrum. Her latest works include augmented reality, holograms, and data sonification as applied to astrophysics data sets. Kim has co-written several popular science books, including 2 children's books. Now, please welcome Arcand.
Great. Thank you so much, Matt. It's so nice to be here with everybody. I'm just seeing everybody in the chat where folks are from. Lots of places that I'm very familiar with, obviously Massachusetts folks, but Phoenix, Arizona as well, Port Orchard, Washington, Ocean Pines, Maryland. Wonderful. It's so great to be here with you all. I am just going to take a second to share my screen. And there we go. Great. So hopefully y'all can see that pretty well. I'm going to talk about light today, the visual spectrum and beyond. I've worked in astronomy for 26 years, as Matt said, so I will clearly be focusing my efforts on that. But because I did actually come from a molecular biology background, I like to at least dabble a little bit in it still these days. And I'll try to bring a little bit of that into my talk as well. I have quite a few slides, but hopefully we'll still have plenty of time for questions and answers, because that's always my favorite part, to be honest. So yeah, so I am, again, an author, an astronomer, a visualization scientist. I like to think of myself just as a data storyteller, though, to be honest. Working with data is kind of my jam, and having different kinds of data to work with is very important. So what kinds of data am I talking about? Well, I'm talking about data from various aspects of the electromagnetic spectrum. I'm talking about different kinds of light. Now, we are used to seeing around us the world because of optical light, because our human eyes have adapted over time because of the location of our planet from our sun, the type of star that we have, the type of atmosphere that we have, etc. And so we have a fantastic organ in our eyes that lets us perceive the world around us through optical light. But if we consider optical light in itself as part of the entire electromagnetic spectrum, it's a pretty small part. If you're into music, you can liken it to a piano. It's like middle C and a couple keys on either side, right? If you try to play your favorite piece by Beethoven or your favorite jazz piece, how hard would it be to make a really lovely piece of music with just a few keys? It would be challenging, to say the least. And so you need all of the different keys on your piano. You need all of the different kinds of light in order to create your masterpiece, play your piece of music, or understand the world around you. If you're into more sports analogies, I could liken optical light is kind of like being able to see down the third base line, right? You will know who's on third base and you might be able to see who's coming home. But other than that, you won't know where the players are. You won't know who's at bat. You won't know who's pitching. You won't know what's happening in the outfield. And if you don't know the rules of the game, it's going to be very tricky to figure out what's happening. So having access to the entire ball field, right, all of the different kinds of light versus just optical light, that little sliver, it gives you a much better opportunity to understand the world, the universe around you. So let's take a closer look at the electromagnetic spectrum. What kinds of light are we talking about? We're talking about the full gamut from radio waves all the way up to gamma rays. Now, I work primarily with X-ray data, but I also do incorporate a lot of data from telescopes like the Hubble Space Telescope, invisible light, like infrared light from the James Webb Space Telescope, or the recently retired Spitzer Space Telescope, and other instruments as well. So it's like all of these different kinds of light, they are essentially a different tool in our tool belt, if you will, right? They are super friends. Different kinds of light are very important to have because if you're trying to solve something, if you're trying to get something done, having all of the best tools at your disposal is really useful. What I have up in front of me now is just a picture of our sun and the many different kinds of light our own star emits. From very cool, low energy kinds of light to some of the highest energy lights as well. So let's talk a little bit about each kind of light and why they're important. Radio light is the least energetic, that is all the way down on the left on that scale that we just looked at a few minutes ago. Why are we using radio light on Earth? Well, we're using it to do things like MRI, magnetic fields plus radio light equals essentially MRI, getting to understand things like your brain. Very important that we can get pictures inside humans because we can't just, open up our skin every time we want to figure out what's wrong. But we also use radio light, for example, some of our Earth-based dishes to capture that radio information from the universe to understand things like massive jets in very active galaxies. And so these are very different scales of phenomena that we can use the same type of light to help understand. Next, we're going to go up to the microwave light. Now, you're probably familiar with microwave light because of your own microwave in your kitchen that's using microwaves to essentially disturb the water molecules in your food and heat it up fast, which is great. I use that to help make my lunch really fast this afternoon, right? But we can also use them to be able to study our own planet because microwaves will help us sort of peer through things like gas and fog and smoke, for example, so that we can understand the moisture levels of soil in certain areas of our planet so that we can understand what's happening after, say, fires. And it's really, really important to be able to study our own planet, of course, because, well, it's the only planet we've got. But of course, we use microwave light in astronomy as well to study things like Venus. This is an image taken with different kinds of microwave light to be able to understand this very exotic twin, if you will, of Earth, this runaway greenhouse gas situation. And so you could probably think of how microwaves are able to peer through that very gaseous and pressurized atmosphere that Venus has. Infrared light, probably many of you are familiar with as well. You might use infrared light in a little thermometer, for example, to take your temperature of you or your child if someone's sick, right? We also use it as the main communications method in fiber optics, for example. And of course, in the universe, we're using infrared light to study many different areas, such as star formation. This is an image that was just released today. I took the opportunity to put it in this presentation because I thought it was so beautiful. It's a little area of star formation and it's on sort of the edge of our Milky Way galaxy. And you can actually see beautiful little galaxies kind of all around it because you're kind of peering out through parts of the edge of the Milky Way and out further into deeper space. And I thought it was a really gorgeous image. Visible light, of course, we're probably the most familiar with. Visible light is very important for human sight, but we also use different kinds of optical light for things like microscopy. Microscopy uses quite a bit of optical light to be able to peer down at very high-powered, highly magnified ways at some very tiny, tiny things, which again is sort of my first love. So any opportunity I can to stick in a microscopy image, I'm going to take it. And then, of course, the Hubble Space Telescope and many other telescopes, both on ground and in the space as well, have provided us with some of the most beautiful glimpses of the surrounding universe in optical light. And this is an active interacting galaxy system here that kind of looks like a beautiful rose because of all of the pulling and that gravitational pull, if you will, that's being exerted on these galaxies as they interact together. And now we're starting to get into the more high energy light. So we're moving into ultraviolet, right? You might be familiar with ultraviolet mostly because of the sun. We're going to be careful, for example, not to get too much UV radiation from our sun. So we'll put, say, sunscreen on to protect ourselves from that. I certainly have to. But we also use ultraviolet light to be able to sterilize things here on Earth in medical fields. We use it for photo treatments. We use it for many different things around in medicine as well. And so UV light is something very useful on the ground, but it's also useful to study things like stars. And this is just showing some ultraviolet radiation that our own sun emits. And this is stacked over time. So it's not all the UV radiation that we're seeing, but we're seeing a composite of many different captures over time to understand the patterns of some of that radiation. And then, of course, to my personal favorite, X-ray light. X-ray light is a high energy form of light that you probably are used to when you think of X-rays that you might get at the dentist or at the doctor if you've perhaps broken a bone. So it's very useful for peering through the skin and the tissue so that you can see a breakdown at the bone. And the doctor's X-ray machine is sort of, blasting a small dose of radiation at you in order to capture that picture. This is just a fun little image from a friend of mine who uses X-ray machines. She is a doctor during the day and an artist by night, and she puts together these composites of deceased animals as they've been X-rays after, and just makes a really interesting statement. But of course, in outer space, we're using X-rays to study some of the most energetic phenomena that exist in the universe. This image that looks kind of like a cosmic hand, if you will, is showing X-ray light from the Chandra Observatory, and it's essentially a pulsar wind nebula. So it's after a star, it exploded its guts out all over the place, and it formed this beautiful pulsar wind nebula because that dead core of the star is spinning around at an incredible rate and stirring up all of this material around it. So we can use X-ray light in the universe to study many different kinds of high energy phenomena and other things as well. And then, of course, the highest of all would be gamma rays. Now, here on Earth, gamma rays are actually very important for cancer treatment specifically, and typically they're good for doing very specific doses on brain tumors, for example. Because the way they're used, it's an efficient way to attack tumors and not attack the healthy skin of the brain. But of course, on Earth, that's important. But beyond Earth, we're looking at things like some of the most energetic objects and phenomena out there in the universe. So gamma ray bursts, for example, and just overall other gamma ray types of phenomena. So there's quite a range of different kinds of objects that these different kinds of light are useful, both on the Earth, but also in space. And so I think this idea of light is important because there's different properties that light has, right? So light has a very particular speed, for example, and we measure distance in light. So the distance for a light year is essentially the distance that light travels in any year, which is about 10 trillion kilometers. And that's a really important marker for astronomers because at very large distance, miles and kilometers break down very quickly, right? When you're going back 13 billion light years, for example. Light essentially can bounce. That is reflection. And whether it's reflection here on Earth or a reflection nebula up in space, light can bend. And whether that's bending to cause a rainbow here on Earth or bending of light because of gravitational lensing up in space, light is absorbed. And so that's how we're seeing all this green color, for example, in this image. And we can also use the absorption of light to understand things like stars or even things like exoplanets, which are planets beyond our solar system because they are orbiting these stars, and those dips in light we can better understand. And then, of course, light is blocked. That's how we get shadows here on Earth. And we can also study things because of blocked light up in space, such as when we're studying eclipses or transits of some kind. So these various properties of light that are interesting for us here on Earth are also incredibly interesting up in space. And hopefully you're not hearing my dogs bark, but they are a little grumpy. So let me know if that gets too loud. Anyway, so how do we study light in the distant cosmos? We're doing it to look at things like exploding stars. We are using light to study things like the areas around black holes. We are using light to study things like galaxies that collide and many other different types of objects as well. But we just have to sit back for a moment and kind of think, right? We are here on this planet, and most of our telescopes or satellites are very close, right? So we are all just kind of here near Earth or on Earth ourselves. And we understand the universe around us by studying light just from this view, right? It's pretty incredible that we're able to study some of the most distant galaxies dating back to the earliest part of the universe by being here on Earth and just studying the light that we're able to detect. So how do we do this? Well, we have very special different kinds of spacecraft that are detecting different kinds of light, as I mentioned. And because they're all detecting different kinds of light, they actually need to have very different kinds of sensitive detectors and equipment on board. So the Chandra Observatory that I get to work for example, is studying X-ray light. And for that, you need very special mirrors and detectors. For the mirrors, they have to be barrel shaped because X-rays would essentially just be absorbed into the wall. It's like shooting a bullet into a wall, right? You have to instead use a ricochet, a grazing angle, if you will, in order to capture that X-ray light down at the bottom of the telescope. Then we have other telescopes, like the James Webb Space Telescope, for example, that have these huge mirrors that are collecting tons and tons of infrared information from the universe to give us exquisite images. We have the Hubble Space Telescope that looks primarily in visible light, but also actually looks a little bit in ultraviolet light and a little bit in infrared light as well. And then we have telescopes like the recently retired Spitzer Space Telescope that also looked in infrared like the James Webb, but slightly cooler, longer wavelengths of light. And so we have all of these different kinds of tools to adapt. And why do we need them all? Like, what does it really matter? Well, I'd like to step us through just an example of looking at one object across these different kinds of light. It's one of my favorite galaxies. It's called M51. It's also nicknamed the Whirlpool Galaxy, and you'll see why in a second. So we're going to look at this galaxy in X-ray light. Now we're seeing, again, some of that highest energy material. We're seeing lots of superheated gas. We're seeing things like exploded stars. We're seeing the very high-powered supermassive black hole at its core, smaller black holes, X-ray binaries, for example, and other exotic phenomena, if you will. Now, if we look at that in ultraviolet light, now we're seeing slightly cooler material than the X-ray light. We're seeing higher populations of energetic stars. We're starting to see a little bit more of the spiral structure of those arms, for example, but they really don't become super clear until we look at it in optical light. Now we're seeing a lot of the dust, and we're starting to see more of the gas, if you will, and we're seeing those dust lanes start to really appear. And then finally, when we look at it in infrared light, now we're kind of peering down through some of like almost like the bones structure of the galaxy, if you will, like that really cool layer of gas and dust. And so each of these slices is really important because they're all adding their own part of the story. No one telescope is going to tell us enough about it. We're more used to looking at things in optical light, so that image will look comfortable maybe to us. It'll look more familiar. But to an astronomer, each of these different slices of light is uniquely beautiful, right? It's beautiful in its own way because it's offering very specific information. And now when we pop them all together, we get to understand this object in a better way. And so if you paid attention to the color selections from the previous slide, you can probably clearly make out that there is a very specific red spiral structure of that cool gas and dust that we saw in the infrared, right? And you're seeing a strong pickup of green along those spiral arms from the optical. And then you're seeing the highest energy, I think, very clearly with all of those little splashes of purple. And then the ultraviolet you're seeing in those cooler blue colors, right? And they're just really well harmonized to show you those pockets of information that it's important to have those different types of light, because no one telescope can tell you everything about it. Let's look at another example. This is an object called Cassiopeia A. It's one of my favorite kinds of objects in the universe. It's a supernova remnant. It's a star about 8 to 10 times the mass of our own sun that ran out of fuel. Its core collapsed, and then it exploded its guts out all over the universe. And we can look at that area with the Hubble Space Telescope and see some of this beautiful filamentary structure around the 10,000 degree mark. And then we can look at that same exact patch of sky in X-ray. And now we're looking at millions of degrees. And you're seeing all of that beautiful stellar debris picked out. Actually, the colors are representing the chemical emissions. And so we're seeing packets of iron, for example, in the purple, and we're seeing the high energy shock around that perimeter. It's a wonderful way to understand what a dramatic difference having different kinds of telescopes, studying different kinds of light, can help you fill in the pieces of the puzzle. So we're just going to buckle our seatbelts now, because we're going to go on a brief kind of lightning tour of some of my favorite sights to see in the universe, thanks to light. All of the images that we're going to look at in the next few slides are combinations from different telescopes, and I'll try to pick them out as best as I can. And then again, I'm going to go through them quickly, though we can certainly talk about them a little bit more once we get to the Q&A, though. Let me take a quick sip of water. Okay, I hope you're ready. So one of my favorite places is definitely the Eagle Nebula, also called the Pillars of Creation. In this case, we've got these tall columns of gas and dust where inside baby little fledgling stars are being born. And the Chandra Observatory is also shown in this image, in addition to the infrared light from the James Webb Space Telescope, because Chandra actually helps detect thousands of slightly more mature stars. So stars that are starting, they've started to age out of the earliest part of that nursery. They're a little bit more energetic because they're starting to get like temperamental teenager sort of age, if you will. And so we're detecting those, and all those kind of like bright disco lights that you're seeing. Those are those young stars that Chandra gets to detect. And again, those columns of gas and dust that we're seeing from the infrared. It's just a beautiful, beautiful spot of the sky. But stars and star clusters are fantastic things to study in general. And this is another one of my favorite areas as well. It's called 30 Doradus, also called the Tarantula Nebula, because if you zoom out even further than this view, it looks sort of like it has legs like a spider might. And so in this case, we're looking at the reds and like beiges from the James Webb Space Telescope. And then all of the blue is showing all of the hot gas, mostly from winds from these stars from the Chandra Observatory. And again, it's lovely when you see these separately, because you can really see that the X-ray light fits in perfectly into those empty looking pockets in the infrared light, and they just complement each other very well. Now we're looking at Zeta Ophiuchi, which is kind of like a runaway star. The star is on the move, if you will, and it's causing this beautiful nebulous-like structure that we're looking at in the infrared light. And the Chandra Observatory is detecting the high energy material of that star itself and the bright blue spot on the right. We also get to look at stars that kind of like hang out together and dance. That's what's happening in this system called our Aquarii. Right at the center of that bright white spot right there in the middle of the image, there are two stars that are kind of dancing together. And the fact that they're dancing and interacting, if you will, is causing all of this beautiful nebulous material to be expelled. And it takes the shape of what to me looks like a really lovely bird. So this is a combination of the Chandra data in purple and the Hubble data in like an orange type of color. And then a second sort of close favorite of mine to exploded stars would be planetary nebulas. I like planetary nebulas because they are not really much of anything to do with planets. They are historically named. A long time ago, when they were first recognized as a distinctive class of object, astronomers had much less powered telescopes, and they thought they were just what the word sounds like, nebulas around planets. However, we now know that these are instead like glimpsing at the future of our sun. It's like forecasting what our own sun might look like one day if we were lucky enough to be able to see it. So what that means is stars like our sun that are sort of average sized, not as exciting as stars that can go supernova, right? Our sun can explode like that, but they do change and evolve. And we've had our sun for a good 4 or 5 billion years or so, and we will have it for another 5 billion years or so, I would hope. But eventually, what will happen is that star will start to expand and it'll puff off some of that outer material. And when it's expanding, it will expand probably, well, it'll definitely expand past Venus. I think there's some doubt whether it'll expand all the way to Earth or not. But regardless, we wouldn't want to be around in our solar system when that starts to happen because it wouldn't be a good time for Earth regardless. And then after that sort of expansion stage, this puffy stage begins and it forms these beautiful planetary nebulas that are kind of like snowflakes to me. They're all incredibly gorgeous and unique looking and all just very beautiful. And this one is called IC418 and is a combination of data from Chandra. We're looking at the sort of cyan color from Chandra that's concentrated at the core, again, of that sort of, cranky star that's aging, and then the brighter yellows that's coming from a Hubble Space Telescope. Now we're looking at the Crab Nebula. This is the result of a star that exploded in a supernova. And what's left is this high-powered core of that dead star, and it's a pulsar, and it's causing this, beautiful structure, these rings, if you will, in the X-ray light. We're looking at this from two different kinds of X-ray light, from the Chandra X-ray Observatory and the IXP satellite as well, which is a newer IXP is a newer satellite that also looks at X-rays, but mostly for polarimetry information, polarization, if you will. And then we're going to move on to one last exploded star because I just can't help myself. This one's called W49b. We're looking at a bit of a smorgasbord of light in this case. We've got radio light that is in the purple, I believe. We've got the X-ray light in the blues and the greens, and then we've got the infrared light in the golds. And I think there's also a little additional near optical near infrared, if you will, in the star field. And this is a beautiful star that exploded, not because it was a supernova like the ones we've talked about previously, but it's a type 1a, which means there were two stars hanging out together. One was pulling mass off of the other, caused an explosion, a ruckus, if you will. The friends got into a fight, if you like, and now we're left with this beautiful supernova remnant because of that. And then, of course, there's lots of galaxies out there in the universe as well. It's not all stars. Stars might be some of my favorite, but galaxies are really amazing too. Our own galaxy is pretty awesome. The Milky Way, of course. We have to have bias because we live in it. But there are other really interesting galaxies out there, all sizes and shapes. VV340 is one of my favorites because it's two galaxies that are hanging out together that just look like an exclamation mark or some think a flower. But again, in this image, we're combining two of some of my favorite telescopes, the Chandra Observatory in purple, and the rest is optical light from the Hubble Space Telescope, who's been a good best friend to Chandra for a long time. Oh, I like galaxies, as I mentioned, for many reasons, and galaxies that come together in triptychs and more are really interesting because there is a lot of space in space, but things are attracted to each other. So galaxies that are hanging out together are really cool to see. This is the Cartwheel galaxy. We're looking at X-ray light from Chandra, which is mostly like blue-purple, and then complementary data from the James Webb Space Telescope, a new science bestie, if you will, for Chandra. Is in like the orangey, pink, and white colors. And you can see it's just a beautiful field of galaxies, but there is actual interaction happening between the main galaxy on the right and then the smaller galaxies on the left. And there is actually a bit of a bridge of X-ray light happening between the three of them, if you will, because of some of these interactions. And then one last group of galaxies that I like is called Stephan's Quintet. These are called a quintet because of five galaxies, though there's actually a difference. One of the galaxies is not actually interacting with them in the galaxies themselves. There are actually five galaxies as well. So it's kind of six galaxies. It's a little confusing. But there is, because of this interaction that we're seeing, that is the blue is the X-ray in this case. So it's like that bright cyan. It looks almost like a bridge. It's a shock that's happening because of these galaxies interacting. Galaxies are so massive, right? And there's so much stuff in a galaxy. There's a lot of energy when they interact and a lot of gravitational pull, for example. So this image, with in addition to the Chandra data, is also showing data from the James Webb Space Telescope. Again, I think those two telescopes together just make a really beautiful couple. So let me see. Our next stop is the Cheshire Cat. And this cluster of galaxies, now a cluster of galaxies is essentially when you have tens, if not hundreds, and sometimes even thousands of galaxies that are all sort of in a bath of superheated gas. And so telescopes like Chandra that detect X-rays, that higher energy material, are really useful for looking at clusters of galaxies because they can detect that bath of superheated gas. So in the Cheshire Cat, this is a cluster of galaxies. Chandra's in purple, and the Hubble data is everything else. You can see the galaxies in the center. Some of them look like they're being stretched. We talked very, very briefly earlier about the bending of light. Well, this is gravitational lensing at work. So the galaxies are not actually being stretched. It's just our perspective and the way that the light is being bent, if you will, on its trip out to us. So that's just a selection of some of my favorite sights to see in the universe. I talked a lot about color in those images because we use color to be able to distinguish the different kinds of light. When it comes down to it, everything that we've just looked at, it all started as just a series of ones and zeros. The binary code makes up these images, if you will. When we're capturing this data from outer space, when we're capturing those photons, those packets of energy, the telescopes capture them and then pack it up as essentially ones and zeros, just like a digital suitcase, and then send it to us on the ground. Now, things like X-rays, things like ultraviolet light, things like gamma rays, microwave light, humans can't naturally see any of that. So none of it comes down to us in color. What happens is it's captured because of various filters or various kinds of instruments that the telescope might have. And you can slice it and dice it based on different kinds of information. You can slice it and dice it based on the kind of light, or for example, the chemical emission, or sometimes other things as well. But it all just starts out as ones and zeros, and we have to translate that into something that we can see. Now, why am I talking about this? Because this idea of translating light that we can't see into something we can see is very, very cool, but images are only one part of the story, and there are other things that we can do as well. Because if you'll remember, I mentioned, humans can't see X-rays naturally. I mean, maybe unless you're Superman, but I think even Superman really couldn't see X-rays, I think. Could he? Anyways, point is, we can translate our data in other ways as well. So I'm actually going to play for you a couple sonifications. Data sonification is just the process of translating data into sound. It's another way of studying the universe. I first started getting into data sonification because a dear friend of mine, Wanda Diaz, who is an astronomer and computer scientist, used data sonification to actually study stellar populations, to study the characteristics of stars. And translating it into sound is important for her because she's been blind since she was a teenager. So it is a valid scientific tool, but it can also be used to help communicate information as well. So the first data sonification we're going to listen to is, again, this mathematical translation. We're going to map across the image from left to right. This image is the center of our Milky Way galaxy. It's about the inner, maybe 400 light years or so around the supermassive black hole that's powered at our galaxy's core. And that supermassive black hole is called Sagittarius A star. It's on the lower right in that bright white spot. There's three different kinds of light that we have combined into this image. The infrared light is red. We're going to hear that as a soft piano. Then we've got the optical from Hubble Space Telescope. It's also plus near infrared as well. And that is the yellow, and we're going to hear that as like a plucky violin. And then the highest energy material is the blue and the purple. That's from Chandra, and we're going to hear that as the highest pitched, a glockenspiel. So we're going to progress from left to right, and then as you're listening, listen for some moments where you hear those instruments distinctly, and then listen for some moments where you hear them sort of harmonizing together. And one other thing you might want to listen for is a little crescendo as we move towards the end, and we can talk about that when we're done. So this is kind of like the downtown region of our Milky Way. There's a lot of energy, a lot of hustle and bustle. It's Times Square, right? And hopefully, as you skewed across that image listening, you could hear some of those moments of a lot of density of X-ray light, or you could hear some moments where that violin was really loud and plucky because it was tracing these beautiful arch-like filamentary structures. Or you could hear some moments where the piano was really clear because there was a lot of that cooler infrared gas and dust that had been captured by the Spitzer Space Telescope. And then when we got over to Sagittarius A star, that supermassive black hole, hopefully you heard that crescendo because there is a lot of energy and power in that area. And that density of information, again, is sort of being translated into all of that that volume and that amazing sound quality. So that is just a few of the things to listen for in this piece. I thought I'd play a couple more quick examples. I think I'm decent on time still, but this next one is going back to one that we already looked at earlier. This is the pillars of creation. We're looking at this combination of data from the Hubble Space Telescope now instead of the James Webb Space Telescope. And we've combined it with the Chandra image as well, which I think, as I mentioned, is showing a population of like thousands of young stars. So we're going to scan across this image again from left to right. And it's primarily two sounds that you'll hear. These are synthesized sounds. You hear a sort of, I don't know, a synthesized sound, if you will, of that optical data that's trying to trace the structure of those tall columns of gas and dust. And then you'll hear more distinct like boops, beeps and boops, if you will, that are tracing all of the stars in X-ray light from Chandra. So let's give it a listen. I just think that's really cool. And then the next one is actually one of my favorite images of all time. Now, this image itself maybe looks quite underwhelming, which is why I adore the sonification so much. These sonifications are something that I've worked on with my partners, Matt Russo and Andrew Santaguida, for the past few years, and our partner, Christine Malik, as well. And the idea is to help make this information accessible to people who are blind or low vision, particularly. And so in this image, we've got essentially one of the most important images ever in X-ray astronomy. And that is because it's the Chandra Deep Field, and it's the deepest X-ray image that we've ever taken. So this is the Chandra Deep Field South. And what it is we pointed the Chandra telescope at a small patch of sky for 40 days and 40 nights. Again, deepest X-ray image ever taken. And what we captured was thousands of black holes as far as the eye can see, essentially. These are very beautiful to me, but it looks maybe a little underwhelming in general. It's kind of like a black canvas that has just paint speckles perhaps tossed onto it, but it's scientifically important. And so the idea to help communicate the science differently was very important to me. So in this one, we're going to scan from bottom to the top because it's actually in stereo. I don't think the stereo sound can be communicated across Zoom, but you can listen to it on your own later if you want to listen to it in stereo. And the coloring in this case is from the lowest energy X-rays are colored in red to the highest energy X-rays are colored in blue and the mediums in green. And so that has essentially translated into sound. The lowest sounds are red and the highest sounds are representing the blue, if you will. So let's take a listen. again, the image itself might be a little underwhelming, but I feel like the sonification really kind of helps encapsulate some of all that sciencey goodness that's wrapped up in all of those pretty colored dots. And then the last one that I'm going to play is the Perseus cluster. Now, this one is a little bit different because this is not just a translation of pixels into sound. This is also a translation of a sound that exists into sound, if you will. So in this case, at the very center region of this cluster of galaxies is a supermassive black hole. That supermassive black hole is very powerful and it's burping out into the hot gas around it. That's causing pressure waves, which are sound waves. Now, the Chandra Observatory actually detected that sound waves as ripples in the image. And we did detect that back in like 2003. And the scientists on the project actually calculated that those pressure waves, those sound waves were B flat, about 57 octaves below middle C. Now, there's no hope for humans to hear that for multiple reasons. One, that's way too low for a human to hear. Two, it's way too far. And three, it's also, there's no medium between us and it that would ever, be big enough for us to be able to hear those things. So there's multiple reasons that we can never hear this in actual outer space. So this sonification is not holding up a microphone to the sky, but it is a translation of something that is singing in the universe in a very low note into a way that humans can hear. So when we first released this one, I think about 2 years ago now, this went very viral. It was a very exciting moment because it helped showcase the power of data sonification. But let's play a little snippet and see what you think. Now, this one you might have noticed is the first radar scan that I think I've shown tonight. And it's because of the shape of the object, we needed to make sure that we were tracing along those sound waves in order to depict them. So that radar-like scan was the most important technique that we could do for that. And we, again, took that sound that if you will, that the object is actually making and just tried to bring it back up into the range of human hearing. So that was special. One last sonification. I lied. The last one was not it. This is the last sonification. This is one of my favorite supernovas. It's called Tycho's supernova remnant. And we are going to listen to the difference, I think, between the optical and the X-ray data. So the optical data is just essentially a star field that the supernova remnant is situated in. It's going to be played like a plucky harp sound. Everything else is data from the Chandra Observatory, and you'll hear that as like this synthesized sound. Now we're going to start at the center and we're going to make our way out. But what I want you to listen for is the, to me, immensely pleasing difference between the very perimeter of that supernova remnant. So that shock that you see is a very clear delineation around the exploded star debris, and then the emptiness of space beyond it, and just going to the basic star field that this object kind of resides in. And I really like the contrast of all of the sort of beautiful chaos that higher energy light is showing, and then dropping off to remind you that there's a lot of space in space. So here we go. I think I'm particularly fond of this one, not only because of the incredible drop off from the X-ray to the optical, but also because the harp is a favorite instrument and my daughter played the harp for a year. And I'm very biased to this one. I think it's really beautiful. Um, but essentially, this process of sonification has been a really incredible thing to work on. I am not involved with the album that I've got on the screen, but if anybody is interested, you can actually buy a vinyl copy of this. A record producer came along and scooped up the sonifications and made an album out of them. I do not make money from this, so I'm not, pushing things at you, but I thought it was a very cool way of taking NASA data and making it accessible in a very different way. So I will stop there because I think I want to have some time for questions. But we live in an absolutely beautiful universe, all of these different kinds of light that are necessary to understand the place that we live in. By doing all of those really hard things, by making all of those telescopes and by, bringing them up into space or making really large dishes down here on Earth, by doing these hard things, we've actually learned an awful lot, not only about the universe, but those technologies that took so long to develop have actually benefited us back here on Earth. And I will just end by kind of, rerouting us back to this idea of light and the fact that today when I go to get a mammogram, like that technology has been improved because of telescopes like the Hubble Space Telescope and the Chandra Observatory. And when I go to the dentist or the doctor for an X-ray, the ability of getting the digital X-rays has been improved because of telescopes like the one I work for and others. When you go to the supermarket, your food has been quality controlled thanks to telescopes that like the ones I've mentioned today. So it's this incredible way of being able to be very circuitous, right? Like this fact that it's taken so much effort for us to learn about the universe, and at the end of the day, that just benefits us here on Earth in multiple ways, not just because we're learning about the universe we all live in, but because those technologies can actually benefit us as humans. So yeah, I like to talk about these things. I like to write about these things. As I said to Matt earlier, I'm a huge fan of libraries. I grew up in a library because we did not have a ton of money as a kid. So that's how I like satisfied my book addiction. And I've been a huge fan of libraries ever since. So thank you for welcoming me to yours today.
Thank you so much. This is absolutely fascinating. And I'm a musician, so I'm like
Oh, great.
particularly like fond of all these like the sounds and whatnot. That was super cool. I
Oh,
gotta look into that.
I
Um,
love that.
we do have a ton of questions, so I'll just
Oh,
remind everyone to please send them via the Q&A. But we may also not be able to get to all of them, but I'll try to send them in order and group them if there's like similar ones. Um,
sure.
First one is, how do astronomers assign the colors to depict non-visible energy sources such as X-rays and cosmic rays? Is there an international standard?
I love this question because I think philosophically about this all the time. And we have actually done a lot of research with people to understand what works the best. I can say there is not exactly an international standard, but there is a standard that many of us do use, which is that the lowest energies are assigned to red, and then the highest energies are assigned to blue. Now, that can be fairly limiting because red, green, blue works great for example, color vision. That's how we get computer graphics on our screen and all that. But sometimes you have more than three different kinds of light or three different kinds of information, in which case you have to go beyond red, green, blue. And at that point, it really is about picking the best colors for the data and the scientific story that needs to be told. So to be clear, this is not like scientists sitting there like using, color by numbers and just having a good time pretending to be Bob Ross or something like that, right? It really is about trying to translate something we can't see into something we can see while maintaining all of that scientific information that's captured. Because an image is a beautiful thing. They are stunning things, right? Just the image behind me, I could stare at it all day, and I probably do sometimes. But it's that captured in that is a ton of scientific information, really valuable information. And we're trying to express as much of that as possible. And so sometimes, like I said, you can't just limit yourself to the red, green, blue standard. You have to go bigger, bolder, depending. But we have found that even though it can be confusing to have the highest energy material, like the X-rays and the gamma rays colored in blues, for example, that seems to be, the opposite of what you might think, because most people are like, oh, don't touch that stove, it's red hot, right? But in physics, blue really is the hottest. And so we tend to use that as our standard as well. And the most important thing I found is just being super transparent about it. You just describe what's being done. You talk about how the image was made, and try to communicate the fact that, because I'm wearing a blue shirt now, it's a blue shirt. But my shirt wouldn't be wrong if I had dyed it red instead, right? At the end of the day, it's a shirt. So it's just about being transparent. I hope that helps.
Yeah, that was a great answer. Someone asked, can you, maybe this is kind of in the same star chart, but can you explain how we see the colors of the auroras and the substorms that cause those colors on Earth? And do other
Mhm.
planets in our solar system experience them as well?
So auroras are essentially the result of atomic collisions, and depending on what essentially is being collided and what kind of elements are involved, you'll get different colors, different reactions, if you will. And yes, they do have auroras on other planets, and I find that endlessly fascinating. Chandra has actually studied auroras. Specifically, it's captured the X-ray signature from auroras on Earth, and it's also captured auroras on Jupiter and Saturn. And other telescopes have found those auroras as well and looked at them in different kinds of light. The Hubble Space Telescope has been a workhorse for that, for example, and other telescopes have as well. And I just think it's absolutely fascinating when you think of, all right, so our planets in our solar system have auroras. Seems likely then that other planets on other solar systems, exoplanets, if you will have auroras, just like they most likely have their own comets and their own moons and all of that. And so it really gets you thinking about like how similar is our own planet and solar system to whatever else is out there in the galaxy and in the universe. It's something I could think about for a while.
Yeah,
But there are some weird worlds out there, I will say that. There's nothing quite like Earth yet, that's for sure.
yeah, yeah. Hopefully one day we can find something similar. Um, there's a question about like uh how some of them like the sound is like the run from like left to right or top down. Was there a reason for that?
Yes, 100%. Great question. So, just like when we're creating an image to represent the data and the scientific goodness of that data in the best way possible, the most clear way possible, it's the same thing for the sonification. We're trying to represent the data through sound as accurately and as authentically as possible. So the shape of the image or the shape of the object really matters. So if we did a left to right scan across a spherical object like an exploded star debris field, it will just smear out all of the information. You won't actually be able to understand the sort of shape-based nature of that phenomena. You'll miss a lot of the context, I think is what I'm trying to say. And similarly with images that are like longer, like landscape, if you will, doing a left to right scan makes the most sense for those, because you're going to be able to skew across that data over time. And it's that idea of being able to express data over time that I find very attractive in sonifications, because I have actually noticed things about data that I have worked on quite literally for decades, because listening to something over time is very different than looking at a dense data set all at once over and over again. And so there are different reasons for the scientific integrity, if you will, to do those different things. It's usually, like I said, based on the shape of the phenomena itself, whether it's a planetary nebula, a supernova remnant, a star field, whatever it is, like that cosmic object tells you the first part of the story, and then you have to understand what the second part of the story is, like what is the scientific context overall. I hope that
Yeah,
helps, but yeah.
yeah, absolutely. Makes sense. Um, Somebody was curious if you have information as if the movie industry incorporates any of your sound demonstrations into their products.
Yeah, so yeah, this is a fun question. So we have had a very interesting interest in sonifications. I worked with the Mickey Hart from Dead and Co., formerly
Oh, wow.
Grateful Dead, for example, because the sonifications were inspirational for the Sphere residency that they just had in Las Vegas. My husband and I got to fly out there and see one of the shows, and the space and drums segment of the show, the sonifications were part of the inspo for that segment, which was very exciting. And some of the images were inspirational for the cosmic sort of look and feel of the show as well. And we've had other artists ask for permission to use the sonifications as well. The sonifications, because they're created with NASA funds, they are public domain, so they can be used. We have had a studio approach us to create, like, I don't know what they call it in the biz, but like a database of sounds, if you will, for sound effects and music. I don't know. I'm not a showbiz person, but you know what I'm talking about. Like a way to package sound so that other movie artists can make stuff with it.
Sure.
And so that has happened. I don't know if anything has come of that yet. Like I haven't heard if there's been a sonification in the movie, but we've had folks ask for them to be included in there's like a sleeping app. There's like a meditation app. I love it all. Like the more the merrier to me. Any application of NASA data, we actually have turned some of the sonifications into sheet music so that they can be played, because musicians like yourself, and I'm a former musician, have asked over and over again, can I play this NASA data? And so we try to translate it into a way that could be done. And yeah, to me, all of these ways of experiencing the universe, they're all valid, they're all super cool, and I just love it.
Yeah, I love it too. There's so much appreciation in the comment too. I'll send
Oh,
you
good.
the chat after,
Oh
because
yeah,
I
I'd
think
love
you'll want
that.
to see. Yeah. There's somebody that said that this is kind of like synesthesia, like
Yes.
yeah.
Yes,
Um,
exactly. Yeah. Yeah. I actually do have a friend with that, and they've made that comment before. Yeah.
yeah, super interesting. Well, um, we're about at time, but I don't want to take up too much of your evening. But thank you so much for this fascinating presentation. So many people said this is like one of the best presentations they've seen all year. So thank
That
you.
is so nice of you. I am so happy that you all enjoyed it. You never know. I don't know if this is going to be a fun topic or not. So I'm happy to hear that it was. I enjoyed it.
Yeah. I will send out an email after this program with to everyone who registered and everyone who's here tonight with a link to the recording of the program so you can look it up. And then I think I can send out the link to where these are like public domain on NASA's website too.
That would be great.
Um, and also books are available through the library or through your favorite bookstore. You said before that the uh, the light book had been just issued as paperback.
Yep. Yeah, that was
Yeah,
very exciting for me. That one, the Light book, has been just probably my favorite book I ever wrote. So I'm very excited that there's still enough interest to have another release at it. So yeah, I hope people check it out at the library and let me know what you think.
yeah, absolutely. Well, thank you
No
everyone for
sound in the
coming.
book, though. No sound in the book. Just
Yeah.
images.
Well, thank you so much, Kim. This was awesome, and thank you everyone for attending.
Bye bye.
Have a good evening.